Okay, so in today's class we are going to discuss multicast. Now the multicast on the internet is a little bit like IPv6. It has been proposed, it has been deployed in parts, but it hasn't really taken off. But multicast, the principles behind multicast are still important. So in today's class we will discuss things about multicast from the point of view of the way it's been proposed on the internet in the network layer. But multicast is important regardless. The same principles that we see here can be applied to multicast on the application layer. So the way in the first programming assignment you had everything running on the application layer. You can build systems using multicast on the application layer. Examples are, if you host a chat room. In a chat room, one speaker speaks and everyone else in that chat room receives that information. That is an example of multicast. The question is, should you implement that using point-to-point unicast between speaker and every listener, or should you build a multicast system? So same principles go over there. These days there's a lot of emphasis on groupware. A lot of companies are developing groupware where you participate in either video conferences or real-time conversations or group management of projects. In each of those scenarios, you have the scenario where there are multiple people interested in the same topic, and information has to flow between all receivers. So how do you do that efficiently? And multicast is a way to do that efficiently. And even though multicast on the internet has been a little bit slow in the network layer, multicast on the application layer is taking over fast. And the principles that we learn are very important for multicast on the application layer. So in today's class, we'll talk about multicast routing, and then we'll also talk about reliable multicast. The book really doesn't go into any details of reliable multicast, and reliability in multicast is very different from reliability in unicast. TCP does not exist for multicast, and for a good reason. We'll see what the reasons are. So reliability, congestion control, flow control, all of these things become a little bit more difficult in multicast as compared to unicast. So we'll see what the issues with reliability are, at least, and what are the proposed solutions. So first, let's look at multicast routing. So in this scenario, you have these receivers, end receivers, which want to participate in a multicast group. Those are denoted by the red receiver, red end host. They are connected to routers. And the multicast routing problem statement is to find a tree that connects all the routers which have end hosts that want to receive messages sent to this multicast group. So the gray routers are not, they don't have any receivers connected to them that are part of the multicast group. But in the tree, they have to be there because there is no other path between, let's say, two multicast group connected routers and a non-multicast group connected router. So you have to go through this non-multicast router, and the problem is, given an underlying network topology, you have to find a tree that connects all the routers which have local multicast group members. There are different kinds of trees. There's a source space tree in which a different tree is constructed from each sender to the receivers. So for each sender, there will be a different multicast tree on which the data is forwarded. There are shared trees in which the same tree is used by all group members. So there's a question of economics of multicast. You can implement multicast in one of two ways. Either implement all the algorithms that we'll see which are related to multicast, or simply do a point-to-point unicast between every pairs of receivers. So a good multicast is when the cost per user for multicast falls below the unicast cost. In unicast, the cost is going to remain constant per user as you scale up the number of users. The hope is that with multicast, as the number of users increases, the overhead in implementing multicast falls fast enough so that it's economically viable to do multicast. Yeah.
So are we looking at the cost or the users? I'm sorry? Are we looking at the costs and the time of the users? Unicast cost is constant, but it's right.
It's cost per user.
Right.
It's rising, but it's not changing as with the number of users. The overhead is there with multicast, but as you increase the number of users, the overhead reduces. Okay. So how do you join a multicast group? Well, on the internet, there is this protocol called Internet Group Message Protocol, and the way it works is that in a local area, where let's say you have a LAN and you have these end hosts connected to a router, in the local area, the hosts inform these routers of their desire to join a particular multicast group. And in the wide area, this local router will then interact with other routers who are part of the same multicast group to form a tree, to do all sorts of things like routing, maybe reliable multicast, and other things related to the group management. So again, it's a two-step operation. In the local area, the end hosts talk to the router, and in the wide area, the routers talk to each other. So if you are doing it, let's say on the application layer, you can imagine these routers and end hosts. They could be the same network, the same node itself. It could play a dual role. In the sense, if you know about Kazaa, some nodes are super nodes. Right? They take care of not only serving files but also part of the searching function. Similarly, if you are implementing multicast on the application layer, this role could be played by a normal node, by either all the normal nodes or by some of the normal nodes. But the way it's designed on the internet to work on the network layer, the local host will inform the multicast router that I want to join a particular multicast group, and then the router will talk to other multicast routers. Now, if you remember IPv4 addressing, the class D address is reserved for multicast groups in the class-based addressing scheme, and irrespective of CEDAR, that still holds. So that address, each particular address in that space will identify a multicast group. So you join a multicast group according to the address, and then any packet destined for that particular multicast address will then flow to your unicast address. And multicast routing makes sure that that happens. So in IGMP, a host will send an IGMP report when it wants to join a particular multicast group. So this host now decides I want to join multicast group corresponding to address 224.x.y.z. That message is sent to the router. Now the router knows that one node on my local network wants to join a particular multicast group, and the operation of IGMP is soft state. So the host need not explicitly unjoin a group. The router will periodically query at regular intervals, and hosts belonging to a multicast group must reply to the query. If no one replies, then the router will time that multicast group out and take itself off in the wide area network. So the router periodically queries after someone has joined, are you still interested? Are you still interested? And if no one replies, then the router will take itself off. What if multiple nodes on the local area are interested in the multicast group? Do all of them need to explicitly join? No. So how do you resolve that scenario?
Because once the group is set up, you could just join the group and you know what's going on.
So suppose this node joins. This node also wanted to join, but it won't send an explicit query. That's what you're saying. What happens when this node decides, I don't want to be part of it anymore, but this node is still interested? So what happens is that nodes on a local area network have they implement a random backoff scheme. Whenever a router sends out a query, are you still interested? All the nodes that are interested in that particular multicast group will choose a random backoff time independently. And whenever the backoff timer expires for any one of the nodes, it will send out a query that I am still interested, or a reply to a query that I am still interested. That query is broadcast on the network, and other nodes can listen to that and not send their own reply. So by this way, only one node needs to send out a reply to the query, and this network still stays alive on the multicast network or on the multicast tree. Yeah.
Things can be done in real time. There are
Variations, but so real time as in streaming. Yeah, you do streaming multicast. In fact, streaming multicast on the application layer is another important application. So how do you build multicast trees? As I said earlier, there are two approaches. There's a source-based tree where you have one tree for each source, and then there's a group shared tree where there's a single tree for the entire multicast group, and it could be either a center-based tree, a core-based tree, or a minimal spanning tree, which is a Steiner tree. So let's look at the basic approaches first. In a shortest path tree, we assume that the multicast router will construct a shortest path route from a source to all the other receivers. So where did we see a shortest path algorithm earlier? It was Dijkstra's algorithm. So to construct this tree, you need the knowledge of the entire topology. So if you know all the routers that are part of your multicast group and you know all the link weights, then each router can individually construct the shortest path tree which goes to all the other multicast routers. So very simple application of the unicast routing principle. You know the topology, you know the link weights, you just construct a shortest path tree. The only caveat is that the The tree should contain all the multicast routers, but the paths might contain routers that are not part of the multicast tree. They are not receiving the information themselves, but they have to forward the information. Then there is reverse path forwarding. So in reverse path forwarding, the idea is very simple, and it's similar to what we saw in unicast routing by the flooding approach. What is the idea? Every router will receive multicast packets. It will look at which link that packet arrived from. If that link is on the shortest path back to the sender of this packet, originator of the packet, then this router will flood this packet on all its outgoing links. If not, it will discard this packet. So to look at this operation, we see here. So let's say the source is this node here, router 1. It receives this packet initially from on router 1. It receives the packet from S. Now the shortest path to S from router 1 is clearly this link. I mean, it doesn't have to use any other part of the network. So according to the rule, it's going to flood this packet on all its outgoing links. Okay. Now router R2 and R4, they get this packet on this link, and then they notice that this packet has come on the shortest path back to the source. So according to this rule, they flood the packet again, all the outgoing links. And now what happens is, the same packet which was flooded by R2 comes to R4, and the packet which is flooded by R4 comes to R2. Now R2 and R4 will notice that this packet that has come, which is originated here from the source, is not on the shortest path back to the sender. So they will discard this replicated packet, right? So they get a duplicate copy, but they're not going to forward that duplicate copy along. So there's not going to be an exponential explosion of the packets. Because it is not coming on the shortest path back, they receive this packet and just discard it. And this process continues. So in this way, the packet ultimately reaches every router in the network which is part of the multicast group. Actually, this packet will reach every router in the network, regardless of whether it's part of the multicast group or not. It will reach this router R7. This router R7 has no hosts attached, it's a gray router, but still it's going to receive the packet. Now where could this be problematic? Well, it's a problem if your network has asymmetric links. Right? So in asymmetric link, a link between two routers, the cost is not the same in both directions. So the shortest path back to the source may not be the shortest path forward to this router. And in that scenario, this technique doesn't work. Do you see that? Suppose it receives the packet here. Now it knows that router 2, the shortest path from router 2 to the source goes through router 1. But for router 1, the shortest path might be something else. This link might have a weight much larger than the reverse link. So router 1 in its unicast routing might be using some other path. This whole notion of reverse path forwarding depends on the idea that the links are symmetric. The forward path has the same weight as the reverse path. If that's not the case, then this could lead to problems. Now, as I said earlier, this in reverse path forwarding, this packet reaches all the routers in the network, regardless of the fact whether they are part of the multicast group or not. And what you do is you send prune messages upstream. So if this router R7 has nothing connected downstream, it's going to send a prune message upstream to the router it received the multicast packet from, and it will tell that router that I'm not interested in this multicast group, do not send me the packets. So then the router R5 will just update its forwarding rule. It will flood on all the links except where it has received a prune message. So this way, over time, the packets will not reach the entire network, but only the part of the network that is interested in this message. Yeah.
Send to R5. Depends
Between R6 and R5.
R5C also has no upstream group members. Yeah, so R5 will also send a group message. Will forward it to R4 or choose to. I'm sorry? R5 will forward it to R4. Yeah, R5 will forward it to R4.
So the first prune message comes from R7 to R5. Now if R5 had a downstream router, then it won't send a prune message upstream, because it can stop the forwarding right here. Because R5 also doesn't have anything. R6 is receiving it through R2. It can send a prune message upstream. So in the next iteration, these two would be removed. So your tree would consist only of R1, R2, R4, R3, R6. Now in a shared tree, there is this problem of Steiner tree construction, which is the minimum cost tree which connects all routers with attached group members. So given a graph, given a subset of nodes, you have to construct a tree which is minimum cost and that connects all the routers. This problem is NP complete. There are approximation algorithms, but it's not used in practice because the approximation algorithms themselves are very complex computationally, and whenever a router joins or leaves, you have to rerun the whole algorithm. So in a multicast session where the membership is dynamic, nodes can come in and leave at any time, it's not feasible or practical to run Steiner tree algorithms. So it's not used in practice. But what's used in practice is in a shared tree mechanism is a center-based tree approach. So in a center-based tree approach, there is a single delivery tree which is shared by all the routers or all the nodes which are part of the network. Now one router is identified as the center of the tree, or also as, you can think of it as the rendezvous point. So if you want to join a particular multicast group, a rendezvous point is identified for that multicast group, and the router which is interested in joining that multicast group will send a unicast join message to that rendezvous point or the center router. This join message is processed by the intermediate routers and forwarded towards sender, because this this particular router that wants to join the network, the multicast group, it probably doesn't have a direct link to the core. So all along the path that this join message goes, it has to be interpreted by the intermediate routers. They have to know that they have to be part of this path. So they also join this tree. And the path taken by this join message becomes a branch of the tree for this new router. So as this join message propagates, all those nodes become part of this tree. And this process is taken by all the routers that join this multicast group. So again, if R6 in this topology is the rendezvous point for this multicast group, and R1, R3, R4 want to join, then R3 will send a direct join message to R6. It becomes part of this tree. R1 sends a message, or R4 sends a message. The unicast path goes through R5. R5 itself does not have any nodes which want to join this multicast group, but because it's in the unicast path of the multicast router, it has to join the tree. Later R1 also joins, but R4 is already part of it. So the unicast path followed by the join message becomes part of the tree. So any node joining anytime else, the join message defines the tree and makes it part of the multicast group. And every message goes to this rendezvous point, R6. So in internet, multicast routing was implemented using DVMRP. Now it's a distance vector. It's a distance vector multicast routing protocol. It uses reverse path forwarding, which we saw earlier, and source based trees. So each source has its own tree. The reverse path forwarding is based on DVMRP's own routing tables. So DVMRP will have its own distance vector tables between the multicast routers, and it's done the same way you do distance vector for unicast routers, only here the multicast routers are communicating with each other. So it's not using the underlying unicast routing protocol, but it has its own distance vector tables. So you just ignore what's happening in the underlying unicast. The initial packet to the multicast group is flooded everywhere using reverse path forwarding. Routers that do not want to join this group will send prune messages upstream. So how do routers know whether they want to be part of this group or not? Well, they are going to use IGMP within the local network to check if anyone wants to be part of this group. If no one replies, then they are going to send a prune message. So it starts by flooding and then it prunes. That's what DVMRP does. DVMRP is also soft state. So the pruning itself is soft state. So the soft state that works in DVMRP is kind of the inverse of the soft state that works with IGMP. So in the local area network, your IGMP, the router which is checking end hosts whether they want to be part of the network or not, they periodically ask. If they want to be part of it, then it stays on. Otherwise, this router takes itself off from the multicast group. With DVMRP, the router periodically asks downstream routers whether they want to be pruned or not, or the downstream routers will send a message upstream that I don't want to be part of this multicast group. If they do not receive this message, then DVMRP will forget branches that are pruned and make them part of the multicast group again. So it will start flooding on the links that had been pruned earlier. So here the default is to forward, and in the local area network, the default is to not forward. And soft state takes care of both scenarios, when to forward and when to forget. DVMRP is it's implemented in most commercial routers from Cisco. And MBone is an overlay network developed on Internet and Internet 2, primarily research institutions, multicast backbone, and that uses DVMRP to multicast streaming media presentations. So a lot of conferences will have their the talks broadcast live on the internet, but it's broadcast using multicast and using this MBone framework, which uses DVMRP. So that happens on the network layer, but again it's not very common. Yeah.
I'm not clear about why, if a router prunes and is off the multicast group, then when would it add them again? Like when would it add them again?
So if it doesn't receive a message from a branch that has been pruned, that I still want to be pruned, then it will add them again. So whenever the soft state timer around 1 minute expires, and it has not heard from the downstream writer that it wants to be pruned, then it will simply flood the packet again. Yeah. So that's why it's the inverse process of the local area network. The local area network, you have to continuously send that I want to be part. Here you have to continuously send I don't want to be a part of this, and there are scaling issues involved with both scenarios. Now, if you want to implement multicast on the network layer, the routers have to be capable of understanding all the multicast protocols. So again, like IPv6, if the routers do not understand IPv6, you resort to tunneling between two IPv6 capable routers. So again, here the grey routers correspond to routers that do not understand multicast. The red routers are the ones that understand multicast. So you construct a logical topology of the routers that understand multicast, and any communication between these two routers is tunneled through the routers that do not understand multicast. And that tunneling is done via regular IP unicast. So the packet which is destined for a multicast address is encapsulated in an IP packet which is unicast. And at the end of the tunnel, that multicast packet is extracted and forwarded along as if it was a multicast packet. Yeah.
Before router. Sorry, if it's an only IPv4 router, like it's one of the phone's phone router, then and that was supposed to join the multicast group. How would that work?
See, multicast is part of both IPv4 and IPv6. This is a separate scenario. So see some routers here, let's assume that all of them are IPv4 routers. But even within IPv4 routers, some routers understand multicast, some do not. Previous example of tunneling, we saw some routers that understood IPv6 and some did not. So replace IPv6 in that example by multicast, and it's the same concept. The lowest common denominator is IPv4. We assume that everyone understands IPv4. On top of that, some might understand multicast, which are these routers, and some do not. So IPv6 is not an issue here. Treat multicast as similar to IPv6. Yeah.
So these kind of made a tunnel
Between these two routers. So when you create that tunnel, these two routers know that it has to open up the packet. Because normally, I mean, you won't have an end-to-end connection between routers. It happens between end hosts. When that tunnel is created, you know that at the end of the tunnel, you're going to open up the packet and forward it along. So this tunnel could be a multicast tunnel or an IPv6 tunnel. Now there's another proposal for multicast on the internet, which is protocol independent multicast, or PIM. A protocol independent multicast does not depend on any underlying unicast routing mechanism. It works with all sorts of unicast routing mechanisms. There are two different distribution scenarios here: PIM dense mode and PIM sparse mode. So in dense mode, you assume that there are a lot of nodes which want to be part of this multicast group, and they are closely packed together, and bandwidth is not an issue. In PIM sparse mode, you assume that the number of nodes that are interested in this multicast session is very small compared to the size of the network. So they are very sparsely located, spread out on the network. And you assume that bandwidth is scarce in PIM sparse mode. So from the dense and sparse mode, the assumptions of the network, the way these multicast trees are constructed is, if it's dense, then you assume that all routers want to be part of the multicast group. Like, you start with the assumption that the multicast group is dense. So then you start with the assumption that everyone wants to be part of it unless it wants to be explicitly removed. When it's sparse, you assume that no one wants to be part of this multicast group unless they explicitly join. In dense mode, the construction of the multicast tree is data driven. What do you mean by data driven? You do this reverse path forwarding. As the multicast group data forwards along on the network, the tree is constructed or pruned. In the sparse mode, the multicast group is constructed by the receiver. When the receiver explicitly joins the group, then routers on the path become part of the multicast tree. So here the construction of the multicast tree is based on control messages in the sparse mode, and in the dense mode there are no explicit control messages. The tree is constructed by the data messages, but the pruning is done by control messages. So PIM dense mode again is flood and prune. You send out packets everywhere, similar to DVMRP. What's different from DVMRP is, in DVMRP it has its own distance vector routing protocol. Here in PIM dense mode, it just utilizes whatever the underlying unicast protocol tells it about the shortest path, and uses that to decide whether to flood or not flood. So it works with every or any unicast routing protocol. It doesn't have its own routing protocol. DVMRP has its own distance vector routing protocol. It ignores the unicast routing protocol. It has some more protocol mechanisms for more efficient operation in terms of detecting whether a router is a leaf node router or not, or whether it's upstream from a leaf node. The downstream flooding algorithm is less complicated than DVMRP. That sort of let's ignore that part. In PIM sparse mode, it's similar to the core based tree. A router will send a join message to the rendezvous point, and the intermediate routers will keep this information as the join message propagates along. But this core based tree or center based tree approach is used only for joining a multicast group. Once you are part of the multicast group, then you can switch to source specific trees. In the core based approach, you had a single rendezvous point which let you join this multicast group, and also data delivery was done through this rendezvous point. This rendezvous point let you join, and whenever any node wanted to send a message out to the multicast group, it would send a unicast packet to the rendezvous point, and then the rendezvous point would send the packets across to the tree. Here, this just lets you join the network. Once you're part of the network or the tree, then you can switch to a source based tree. You need not send it to the core or the center. That's sort of the principal difference. So you can switch from a core based distribution to a sender based distribution. Now we'll talk a little bit about reliable multicast. What are the issues with reliable multicast? You need to implement reliability in a variety of scenarios with multicast. What are the techniques that are used for reliable multicast, and how do these techniques scale with the number of receivers, with the heterogeneity in the receivers, and whether this delivery has to be real time or not. And we look at different approaches to reliable multicast. So first problem is identify all the issues involved. So now you have to transfer data reliably from either a single source or a number of sources to a number of receivers, and these number of receivers can range from tens to hundreds to thousands to millions, depending on how popular this multicast group is. Suppose your multicast group is a streaming sports event. You're trying to watch the live telecast of some sports event on the internet. That kind of a multicast session will have hundreds of thousands of receivers. Heterogeneity is another problem. Some of these receivers will have a broadband connection, some of them would be on a dial-up line, some of them would have wireless connection. Each receiver would have different characteristics in terms of bandwidth, loss rate, delay. The reliable multicast protocol has to take care of all of these issues. Reliability semantics could be different. If you have a streaming telecast, then you might be able to lose a few packets and still term that broadcast as or multicast as reliable. If you are trying to do reliable data delivery, then every packet has to reach every receiver. In real time, reliability is also related to the maximum delay a packet can incur. So in some scenarios, even though the packet is eventually delivered, it's delivered after the deadline for the packet is passed, where it's no longer useful for the receiver. If you're trying to do, let's say, a chat session, then reliability also involves delivering the messages in the right order. Right? If user A types something, user B responds to that, user C should see those messages in the right order, B after A. Otherwise, C can get confused about the conversation. If it sees the reply first before, let's say, a question, then the ordering semantics are very important, and that is part of reliability. So heterogeneity, scalability, all kinds of reliable multicast error and congestion approaches have an analogy in human-to-human communication. That's what people say. So some of you are paying attention. So you have an excellent bandwidth between what I'm saying. Some of you are not really following. So you need more bandwidth. Some packets are getting lost. Some of you are not even there. So all of the listeners have to be addressed in this reliable multicast scenario. Yeah. You had a question? So another issue with reliability is that this delivery of data, what does it mean if receivers can come and go? What do you mean by reliable data transfer in that scenario? How do you detect when new receivers have joined and when they have left? What is reliability in that scenario? What is sort of the lag time you can give for a receiver to start receiving the data, and when do you stop sending data to a receiver when the receiver has left? Heterogeneity. So in this scenario, imagine the bandwidth of the link to be the thickness of the LAN. Okay, now you have a bunch of different receivers which are all part of this multicast group, and the sender is trying to send packets to all of them. So in this scenario, this node, which has the sort of the thinnest link back to the receiver, will dictate what the reliability semantics the reliable multicast protocol has to follow. This is known as the crying baby syndrome. Because this receiver needs the most attention, everything that's happening upstream is dictated by this receiver. It has the worst link back, so it will have the most errors. Reliability is dictated by what's happening here. So because of that, this receiver overhead is increased for all other receivers which were receiving these messages properly in any case. So some of you understand a point when I say it the first time, but because I have to repeat for people who don't understand, some of you feel that you're wasting your time. So this is the crying baby syndrome, and this becomes very acute when the number of receivers increases in multicast and you have to implement reliability. So there's a question, what is a socially good policy for reliable multicast? When do you make the trade-off that, okay, I'm not going to give all the attention to the weakest receiver, but have a compromise somewhere? There's a question of feedback implosion. So the way we saw reliability implemented in when we saw reliability in the transport layer, RDT. Well, you sent a packet out and then you got an acknowledgement back. And depending on whether the acknowledgement arrived or not, you took different actions. In multicast, you have 1,000,000 receivers connected to the sender. You send one packet out, it reaches those 1,000,000 receivers, and 1,000,000 ACKs come back. Then what you have at the sender is an ACK implosion. The sender cannot possibly process all these ACKs. So ACK-based schemes are very difficult to implement for reliable multicast. So the way reliability is achieved is through a mixture of ACKs and NACKs. ACKs have this problem of implosion, so you have to do ACKs and NACKs. And another very important technique which is used in multicast is forward error correction. So we'll see the concrete examples of forward error correction when we start doing link layer protocols from the next lecture. But I'll give you a sampling of what happens with FEC in reliable multicast. The issues that are involved with achieving reliability is to whom do we send the ACKs, NACKs or FEC packets. These ACKs or NACKs can either travel back all the way to the sender, or they could be processed locally or hierarchically, and that can improve efficiency. Again, there's another question whether these ACKs, NACKs should be multicast to the group, or are they unicast back to the sender. Both have their trade-offs. So if you have sender oriented reliable multicast, then the sender will multicast all retransmissions. It implements selective repeat, and timers are used for loss detection. In this scenario, you have ACKs. So you're not using NACKs. The sender sends the packets out. One receiver does not receive the packet. ACKs come back. The sender keeps an ACK table. The ACK table will time out because an ACK never came from this receiver. Then the sender has to multicast that packet again. Now this scenario is clearly not scalable. If you have lots of receivers in your multicast group, then keeping state of all the ACKs is not possible at the sender. If you have small multicast groups, then maybe you can implement the sender oriented reliable multicast. But this approach does not scale. In receiver oriented reliable multicast, the sender is not going to keep any state. All the states are kept at the receivers. The sender will respond to NACKs, and these NACKs are unicast to the sender to detect missing packets, and each receiver will have a timer to detect loss transmission. Now it's also easier in this scenario to allow for joins and leaves, because the responsibility is shifted to the receiver. A receiver can leave, and the sender does not have to update its state table. It doesn't have to keep track. All the responsibility of reliability lies at the receiver. So the semantics can also be decided by the receiver. Suppose that the receiver is not interested in every packet. It's receiving a streaming media broadcast, and if the quality is acceptable, it may not request all the packets. So in this scenario, if the packet gets lost, the receiver is going to unicast the NACK back, and then the sender multicast it back. So there's one small issue with receiver oriented reliable multicast. I mean, it scales. Receivers can decide their own reliability semantics, but the sender, it has to release this data which is received by all. Right? Sender has to keep the data in its buffer ready to transmit. When does it take that data out from the buffer? That is an important issue that has to be addressed. Because when does it know that everyone has received the data? When does it know that NACs will stop arriving for a particular data packet? That is an issue that has to be addressed by receiver oriented reliable multicast. The sender does need to keep some state. It's very minimal, but it does need to keep some state, and this timing issue is very important. How long do you hold on to the data before you are sure that no NACs will arrive for this packet? In the forward error correction scenario, are you familiar with forward error correction coding? So in forward error correction coding, you have you add redundancy to the data that you are transmitting, and that redundancy helps you recover from losses. So there's this, an example is Reed-Solomon erasure code. What you do is, in a k encode, for every k data packets, you're going to construct n minus k parity packets. And you can recover all the data packets if there are no more than n minus k losses. And these n minus k losses can occur anywhere. They could be either the parity packets or the data packets. But if not more than n minus k get lost, then you can recover the entire data. So a very simple example is this scenario. So here is a sender which is sending out 3 data packets, D1, D2, D3. There are 3 different receivers and they all lose different data packets. Now if you are not implementing forward error correction, you would have to send out all the packets again so that all the receivers receive this packet. If you are simply doing data retransmission. Now what you do is you construct a parity packet which is D1 exclusive OR, D2 exclusive OR, D3. This is the parity packet P. This parity packet P can help you recover all the different data packets at different receivers. So what is A exclusive OR A? 0. So if you have A exclusive OR B, and you have B, can you recover A? If you're given these 2 bits, can you recover A? Right? You can recover A. If you're given these 2, can you recover B? Right? So this serves as the parity packet. A and B are transmitted and receivers can lose either B or A. As long as they have this parity packet, they can process this parity packet and the packet that they already have to recover the missing information. That is a very rough idea of forward error correction. So by doing this, you have reduced the retransmission to a third. Instead of retransmitting all the data packets, you are just retransmitting the parity packet, and individual receivers can process and recover whatever has been lost. Now that's the principle of FEC for reliable multicast. Now with scale and heterogeneity, the issues are you want to avoid feedback implosion, you want to avoid receiving unneeded retransmissions, and you want to recover the data quickly if you have a real-time multicast. And some of the techniques that are used are feedback suppression, local recovery, hierarchical recovery, repair servers, and then different multicast groups. So we will take a look at feedback suppression. So in feedback suppression, you're going to randomly delay NACs. So if both of the receivers here lost packets, then instead of immediately sending out a NAC when they detect that there is a loss, they each choose a random timer, and when the random timer expires, the NAC is going to be multicast. So this NAC is multicast. It also goes to the other receiver. So this receiver need not send its own NAC. So this reduces the possibility of feedback implosion. And this is the same idea that is used in IGMP when you want to join a multicast group. Receivers choose a random backoff timer. When the first one expires, it will broadcast its desire to join the multicast group so that the other receivers don't have to send the message. Similar ideas here. Each receiver decides to send the NAC after a random interval. It is broadcast. Broadcast goes to all other receivers. Because these receivers know that this packet has been NAC'd already, they're not going to send their NACs ahead. So this reduces the problem of feedback implosion. And then once the NAC has been received, the data can be multicast again. In local recovery, you allow, yeah. Yeah. Well, not really. I'll come to that. Axe, it becomes a little bit more difficult.
Sending max is less than sending max.
Yeah, you assume that your loss probability is going to be low. So NACS is already one way of reducing feedback implosion. On top of that, you implement that and you get better performance. In local recovery, what you do is you don't send your repair message back to the sender, but you let a nearby receiver on the tree send you the data packet if it already has it. So you ask your neighbor by sending a localized NAC, and this is sort of complementary to feedback suppression. So there are different reliable multicast protocols proposed on the internet. One is SRM, Scalable Reliable Multicast, and then Reliable Multicast Transport Protocol, which is RMTP. They both of them do this local recovery in different ways. SRM does it sort of loosely. In RMTP, you do it in a very strict, organized manner by constructing a tree. So here's an example. Suppose receiver 2 in this tree has detected a lost packet. It's going to multicast a repair request, but this repair request should not be seen by R4. R1 and R3 have the packet that R2 wants. So this repair request goes forward. R1 and R3 again will have their own timers like NAC suppression. R3 will time out first and will send out the request. And it sends out the repair packet back. I mean, was this process clear or? The NAC request is sent on a limited scope. So you're going only asking your neighbors R1 and R3. You don't send this NAC request all the way up to either R4 or to the sender. This NAC request is heard only by R1 and R3. They start their individual timers. When one of them times out, one of them expires, it will send out the repair packet. So in SRM, which is proposed by Berkeley, it uses receiver oriented NAC suppression, again by this timing mechanism, and local recovery. In hierarchical recovery, what you do is you're going to partition receivers into smaller groups. So you have one big multicast session on, and within each multicast session you partition them into smaller groups. Each group will have a designated receiver, and the designated receiver will recover the lost packet for all the group members in that smaller group. So either the designated receiver will have the lost packet, or if it doesn't have, it can send the repair request upstream. And you can do it hierarchically. You can have multiple layers of these smaller groups. So these designated receivers themselves can form another group, and you can partition that group of designated receivers into another group, and that smaller group can have a designated receiver, and this process can continue. So in this way you can scale to millions of receivers, and there is no problem of feedback implosion. By assigning one local group leader or designated receiver, you can cut down on feedback a lot, and you can do local recovery. The key issue here is, of course, how do you build and maintain these smaller groups? And a lot of work has been going on in this area. There's a particular project at University of Maryland called NICE. NICE is it's a recursive acronym, NICE Internet Cooperative Environment. So that lets you build these groups in the application layer hierarchically, and they've used NICE for doing streaming reliable multicast or streaming multicast in the application layer. RMTP, which is the Reliable Multicast Transport Protocol, it imposes a tree structure on the receivers. The top node will control the tree, and nodes which are inside the tree, they aggregate these ACKs or NACKs. And if they have the packet which was requested by a NACK, then they'll do a local recovery. If not, they forward the NACK upstream and hope to get the repair packet from upstream. This RMTP also has support for forward error correction, and they also implement a flow control mechanism. Up until now, we have never talked about the rate at which this data is transmitted on the multicast group. Now, often you have receivers which are very slow. So in RMTP, what you do is the application will declare the minimum and maximum rates. Any receiver which is below the minimum rate required by the application is not allowed to join RMTP. So RMTP also implements flow control in this manner. And then data flows according to the slowest receiver, but which is capable of receiving data above the application minimum. So in network assisted reliable multicast, again that has not been really implemented on the internet. Routers could help by aggregating these control messages. They can filter the repair messages. So what we saw so far, everything was being done by the end host which are connected to the router. Routers can themselves help by aggregating these control messages and also by doing pruning of the repair messages. Routers can buffer these packets that are needed to respond to these ACKs or NACKs. So this again assumes a network model of multicast where the routers are separate from the end host. If you're implementing multicast in the application layer, then the routers or nodes are really the same, and these responsibilities are handled by the nodes. But if you have a strict separation between routers and nodes, then routers can assist by doing some of the job to make it more efficient. So in aggregation, the router will aggregate the NAC message. In subcasting, the router can effectively prune where the data repair packet is going to go. So if this receiver has already received the packet, by looking at the NAC messages arriving, it knows where the repair packet has to go. So it won't duplicate the packet on this link. So the router is assisted in two ways. It assisted in feedback suppression to the source, and it assisted in efficient repair broadcast. So it's not going to send the repair packet to all the nodes that do not require it. It sends only to the nodes that require it by looking at the NAC messages that have flown on top. So all these principles apply to general multicast, not only internet multicast or multicast implemented on the network layer. These same principles apply if you are going to implement a groupware or a chat system or a streaming system on the application layer. So we'll stop here.